Okay, welcome everybody. This is double entry accounting at scale. I'm Alex Mooney. I used to be a physicist. I went from programming for science purposes into web developer kind of programming about 8 years ago. I currently work on the ledgers team at Modern Treasury. The ledgers team builds a ledger as an API like a service. We have like double entry accounting and lots of features. And you can get my contact information here. It's also going to be on the last slide, so don't feel like you have to quickly grab your camera or anything. So in this talk, we're going to start by kind of giving a very cursory overview of what double entry accounting is, and then we're going to build the tables and the SQL kind of modeling that you would need to build a ledger. We're going to talk about the performance implications of building a ledger in the way that we describe, how you can extend the performance beyond like a typical relational database use case through what I call here like a hybrid asynchronous API. And then I'm going to talk about like care and feeding of a ledger system, especially with the complication that comes along with the asynchronous work that I'm going to kind of talk about. And without any further ado, we'll get into double entry accounting. So double entry accounting was invented in like the 13th century by like Florentine merchants to track their trades in the marketplaces. But it really doesn't have to be complicated. The idea is that every time you move money, you have to just obey a few rules. And the rules are that you have to have at least 2 accounts involved. You have to debit from one account and credit to another account. There has to be at least one of each of those. And that the total amount of debits and the total amount of credits equal one another. And so you may or may not be familiar with this like debit and credit terminology, but what this all boils down to is none of us are the Federal Reserve. We don't get to create new money. We also don't get to destroy money, and we wouldn't want to, even if we could. What we can do is move money from one account to another. So like debits and credits adding up just means that like no money is being created, no money is being destroyed. And that's basically all you need to do for double entry accounting is think of all money of movements. You don't just have one account balance that you're adding 100 to. You have to also track the account that $100 came from. So the talk is called double entry accounting at scale. And I'm going to jump like way ahead to the midpoint of the talk when we find out that the way that we're going to build up this ledger is going to have a performance problem, because I don't want anyone to be surprised. Basically, a traditional implementation of a double entry system in something like Postgres or MySQL, any relational database, is going to have a performance issue. And it's because we're going to have like rows in the database that are tracking account balances. And every time you move money into or out of an account, you're going to need to update that balance. And because you're doing row-level updates, databases have row-level locks, and that means only one update can hit a particular row at a time. So updates have to be done serially. And even if you build like a very big database instance that can handle lots of work, there's still only like one writer at a time, and that is going to cause a throughput bottleneck. And the bottleneck is quite modest. You're only going to get tens of updates per row per second. And that's why we're ultimately going to go to hybrid. So with all of this kind of out of the way, like motivating us towards the technical vision, now we'll get our motivation for kind of why and how we're going to be tracking things with a ledger. So we're going to pretend that we're going to start a business somewhat like Venmo. We're going to have lots and lots of user accounts. All of them can have account balances, and they can move money between each other. They can pay into our system with external funding sources. They can draw money out of our system. The product team has a few really key feature requirements for us as we're designing our system. We want to be able to generate a history of how all of the money has moved through the account so that we can ultimately like give our users balance statements of like, hey, you paid in $100 on this day, then you spent $12 on that day. That's why your balance is $88 or whatever it is. We need to make sure that we're enforcing this like conservation of money that we talked about with double entry accounting. As a former scientist, I still have a love for conservation laws, very significant for making any kind of reasonable accounting system. And the third requirement is we want to make sure that users cannot spend more money than what they have. So in some systems, you might imagine you're going to apply like fees to user amounts and you could draw the total balance to negative, but we want the ability at least to enforce conditional spends. So those are our three like hard requirements for what we need our ledger to be able to do. And so we're going to start by building a couple of tables. An account table for now is just going to hold an ID. And then we have an entry table, and entries tie into an account and they describe the amount of money. So when you have a whole bunch of different entries, you can imagine like summing them all up, and that would give you the account's balance. And this kind of already gives you the idea of the account history that we needed in our first requirement from the product team. You could look through all of your different entries and arrive at the total balance for any particular point in time. Those of you who are a little bit more familiar with double entry accounting may be rolling your eyes at me at this point. I need to at least acknowledge that this is a simplification. So real double entry accounting is going to have like an account normality and track credits and debits independently of each other. And if you have like a credit normal account, you add all the credits and you subtract all the debits to arrive at the balance. And this is basically all historical because in the 13th century, they weren't using negative numbers. They didn't believe that they were real. For the sake of talking to my fellow developers, I imagine you guys are a lot more comfortable with negative numbers than you are with credits and debits. We're just going to track amount, and we're going to treat some of the amounts as negative. It's a simplification. If you were going to build a ledger like this, you need to make sure you talk to your finance team and everyone else who is going to be like consuming the ledger data and make sure that everyone's on the same page. They probably will want you to actually do like the right way of doing accounting, but we'll keep it simple for this. So next, we want to make sure that we have our proper double entry accounting. We're going to build another table called transaction. So a transaction is an overall money movement. An entry belongs to a transaction and to an account. So within each transaction, we're going to sum up all of the amounts on all of the entries and make sure they add up to 0. And this is like pretty simple application level logic to make sure that your double entry accounting rules are being obeyed at all times. And next, we're going to run into problems here. If we only have the amount on the entry, this is going to be fine until we start getting many thousands of entries on one particular account. At that point, whenever we want to get the balance, we have to like dispatch a fairly expensive SQL query to sum every entry together. So we're going to save ourselves a lot of database work, and we're going to add a balance to the account table. So this is just like the rolling sum, and we're going to update that row. As I've kind of mentioned earlier in the talk, this is going to give rise to a little bit of a problem. But it also allows us to set up a very simple conditional transaction SQL. And this is going to give us that third requirement we had talked about where users can't spend more money than they have, because we're going to update the balances. And as we update the balance on an account, we can also use a where condition in SQL and check that the resulting balance, so this example is a user is spending like $10 denoted in cents, so 1,000 cents. We update their balance to their current balance minus 1,000, and we specify that the balance minus 1,000 is greater than or equal to 0. And we use this returning clause out of the SQL so that we get back a row that is the resulting account balance for this account if the SQL succeeds. But if the balance is insufficient to meet this where condition, we don't get back any rows at all. And so we can atomically update the balance only in the case where the user actually meets this requirement. So this is a race condition proof solution to making sure that the user can't double spend. Even if they send their transaction into 2 different web servers simultaneously, the database has ACID guarantees. And so the A in ACID stands for atomic. This will either completely succeed or completely fail, and we're safe from users being able to overdraw their accounts. But now we have the balance stored in 2 places, and we need to be able to reason about the total account balance in a reliable kind of way. And keep in mind, like, if your product is successful, you're going to get new entries being added in basically constantly as a stream. So if you read the account balance and it says that it has 1,000 in it at some point in time, you then go and read the entries so that you can generate like a user transaction statement, and you find that now you have 2 entries and the amounts don't add up to the balance amount. So that's because in this example, like, the entry on the right was added in between your 2 calls to the API, and you're in this condition where you can't fully tie your entries back into a balance because, you know, now you have like 2 sources of truth. The real source of truth for an account's balance should only be the entries. Those are the things that you're validating that your total amount of money has followed double entry accounting rules. So what we're going to do to overcome this and make it so that it's unambiguous which entries belong to a particular balance is we're going to add a version onto the account. And the entries get a corresponding account version column. So now if you read that balance and it says, I am version number 1 and I have 1,000, then you read the entries and you'll see an entry with version 1, an entry with version 2, and you'll know that the version 2 entry was not included in your balance read because it was above your version. And so now we use this and we update the SQL I showed you a moment ago. Basically, we do the same thing, but now every time we update an account's balance, we're also going to increment the version. And we're going to return the version out of the SQL as well. So we get the resulting balance back. That's probably going to be useful to display to your user in some API response. But the version that we return here, we use to set the entry's account version. So your entries will always be tied back to your balances. Anytime you read a balance, you'll have a version. It'll be completely unambiguous what was included and what wasn't. So this is all the data modeling that we're going to need. And now we'll take a moment to like imagine using this API a little bit. So we'll post to the account up there in the top right. We get a response back. It gives us an ID, and it tells us it's an account, and it has no amount and no version. And on the left, there is our account represented pictorially. Then we can post another account, and we'll pretend this one is like some user's wallet. And then to transact between them, we can post a transaction and then specify like an array of entries. Each entry will have its account ID and an amount. They will automatically get tied together in that pink box at the bottom. We'll automatically form a new ledger, a new transaction that ties together the entries and makes sure that they're valid. And it's a little bit small, but you can see that the balances are being adjusted according to the entries, and that the versions in the purple boxes match the account versions in the green entry boxes. So then this is like a user paying $50 into their account. If we imagine that they withdraw 10 or they're spending it, we can add this balance greater than or equal to 0 kind of message to the JSON to indicate this is a kind of transaction where one of the accounts is not allowed to overdraw. You probably want to not bake in those balance rules into your core API because, again, like, there might be business reasons why an account will get drawn to negative numbers, like you're assessing some kind of fees. So I would recommend that you have like this imperative choice to opt into any kind of balance limits that you want to enforce. I think in some cases, you might also have like upper balance limits, and you could imagine with this format, you have greater than or equal to 0, but also less than or equal to 50,000 or something, if you don't want your balances to go above a certain amount. Very simple. And so here, you can see that the versions have updated to 2, and the new entries have account version 2. Very simple. And then when the user tries to spend more than what is in their account, also very simple, you just kind of respond with a 422 saying that like the balance was outside the range that you specified, no entries get created, no transaction is created, there's no new account version. Basically, it was like it never happened. So with all of this in mind and how we use the API, now I'm going to show you some performance data that I gathered by spinning up an API like this, pointing it at a production-like database. Like, it was a reasonably sized AWS instance, and I measured how the database transactions flow through the system with different numbers of users. So the timing data is going to be when I open a database transaction. And so this is an annoying point of terminology in that I've called the money movements transactions because it's a fairly common name. We also have a database level transaction, and that is like when you tell the database to begin, and then you issue some statements, and then you tell it to commit, database transaction. Anyway, so we'll be measuring the duration in which a database transaction is open. We'll measure the statement that actually updates the account balance, the SQL that I've been showing you a couple of times. And then we'll also measure like exactly when the database transaction commits. So I gathered this data using an open source tool called Locust that I feel compelled to shout out. It's a great tool. You can write user agents in Python, and then your laptop or whatever you want to use will just spin up lots of little micro threads, and they will be able to execute whatever script that you specify, which is usually just calling your API with some kind of parameters. In this case, it's like randomly choosing between some of the accounts that I created and randomly generating amounts. You can make Locust scripts very sophisticated to capture like actual user interactions in your app with like, we expect a user to visit this page, and then after between 5 and 15 seconds, they'll click over to that page. But this is a very simple case. We're just like repeatedly transacting in the way that I've already shown you. So these charts are Gantt charts, so they're like timelines going to the right. Each strip is 700 milliseconds wide, and then it's divided into 3 rows. The green row is the time in which a database transaction is open. The pink row in the middle is the time in which we're updating that account's balance, and you see that it's very fast. It only takes a few milliseconds. And then the purple bar at the bottom is when I'm asking the database to commit. So of course, I'm getting these timestamps out of my application code. So the purple bar represents like the line before I told the database to commit to the line after. So somewhere in the purple bar is when like the database thinks it's committed, but this is like the best timing I could get from the stuff. So you see, like with one user, there's plenty of time in between requests. Everything goes through quite fast. With 2 users, it so happens that the traffic is interleaving and not interfering with itself. So everything is still quite happy. But you can run into a situation where your 2 users, their requests happen to come in at basically the same time. And you see that those pink bars suddenly get kind of slow and wide. This is because your second transaction that comes in, which is like the lower of the 2 green bars, the one further to the right, that has to wait on the previous request to commit before it can actually run that update statement. This is because of the row-level locking issue I mentioned at the beginning of the talk. And so this is just like 2 users where the requests happen to kind of like interfere in a bad way. But as you start ramping up your API and getting more and more traffic, this becomes like the norm where every request is waiting on something else. This is, I think, 4 users running against the same account at the same time. And we call this like the hot account problem because one of the accounts is getting used in every transaction. And so every transaction has to wait on another one to complete. All of them want to update the same row. And so this is like a common kind of account pattern in accounting. You can imagine that there is an account that represents all of the cash in your system. So every time a user pays in or cashes out, you have to update that one account. Whereas like if user A is paying user B, you only have to update those 2 accounts. And they're not going to transact with a whole lot of frequency. So the top chart shows what I've already been showing with like big, long transactions. The bottom chart here is the same data. I've just stacked the first 4 requests, so it's like more obvious exactly why it's waiting. You can see that each request's update statement, the pink line, ends only when the previous request has actually committed. So this is just the illustration of how that problem like comes in and how it just gets worse and worse as you put more traffic in. So this is the total amount of time that it takes to run a web request versus the number of requests per second. And you see it's basically happy until we get up to 25 or so requests. And then it doesn't matter how many more requests I throw in. All they do is get slower and slower as they continue to wait on each other. This like hockey stick really kind of does go asymptotically to infinity. the way I had it set up for this particular test, I can't run more than about 26 requests per second because it takes 1/26th of a second to go from the account update to the commit. So that is our hard limitation. To get around this, we're going to build an asynchronous workflow that we can shunt some of our traffic into. So there is a nice property of the system that we're describing. Well, there's like a few properties that all come together that make them amenable to update in batches. And that is entries update account balances, and the updates are all additive. So it doesn't matter if I have 3 entries for 500 or if I have 1 entry for 1,500. That's the same change, essentially. So you can just add entries together and you'd produce the same results. And also, we put that account version column onto the entry table. And that means we can unambiguously relate when an entry was actually applied to an account balance. And that means we can actually defer applying an entry's amount to the balance. Because if a user fetches the balance of an account and they see a particular version, it doesn't matter if we already have future entries in the database. As long as we haven't told the user that those are included when they're not, everything's happy. So the caveat of this is like, when you're doing the kind of updates that are validating your resulting balance, you cannot batch those. Those have to be processed synchronously, immediately, because whether they succeed or fail determines your API response. So you can't pull that kind of traffic out of the immediate web request. Well, the good news about this is that generally you're doing balance validation on user accounts. And there is no user that I know of who can swipe their credit card faster than 20 times per second. And so the account balance limitation just isn't a problem for them. You really only care about like your platform level accounts, your total cache across your entire system. You don't care about what the total balance is there, so you don't need to get the you don't need to run those validations, and you can defer applying the entries to the running balance sum. So this is how we do it kind of schematically, starting at the top left and kind of working our way clockwise across the diagram. We get a request from a user to create a transaction. Immediately, we land the transaction and the entries in the database. That's like the down arrow. Then we consider each entry. Is this entry synchronous or asynchronous? A synchronous entry is the kind that is going to validate a balance. And for that, we immediately update the account using the SQL that we've been showing. And we fill in the entry's account version. And then we're done. If you have an entry that doesn't need to be processed synchronously, we send it to a queue instead, and that's like to the top right of the diagram. The queue has a poller that listens to it. It just continuously, in like a tight loop, pulls entry information back off of the queue for processing, and then it aggregates together all of the entries which apply to a particular account. So if you have a cash account, every entry on all of the cash accounts is like added together into one pile. Every half second, second, however, whatever polling interval you like, you dispatch all of those entries for a given account as a unit to be processed. One processor for each account that you've seen over the last second that you've been polling the queue. And then we get kind of to the bottom. You have a asynchronous job. All it does is it takes all of the entries that the queue poller found for your account, adds them all together, does the same kind of SQL update, but now instead of updating just one entry's amount, it's updating all of the totals. It takes the resulting version that you get off of the account update SQL, and it attaches that to the entry account version for every entry in the batch. So all of the entries have one common batch version, and you've flushed like dozens or hundreds of entries into the database in one trip instead of one trip per entry. And how well does this approach work? Well, the pink is the chart that I already showed you, where when we get 25 users per second, you just hit a wall and you can't go any faster. This kind of processing, the hot account problem is just completely eliminated in this. Like, if you just keep scaling, of course, you're going to run into different bottlenecks, but they have nothing to do with the row level locking issue that was kind of the heart of why our system fell down earlier. So I need to point out that this isn't like a free kind of thing you can do and it's going to be like easy and happy. There are ways that your queue can fail. You have to be sure that your system is working, even if it does, like, you have to look for failures instead of expecting your system to tell you about them proactively. So we're going to talk about queuing, and then I'm going to give a couple of points about how you can monitor for problems in your system. So the important thing to remember about a queue is it's not an ACID database. You have to treat the messages that come out of it kind of carefully, a little bit skeptically maybe. There's like 3 kind of failure modes that are common. You can imagine the queue giving you the same message more than once. You can imagine the queue never gives you its message at all, or perhaps it gives you its message, but it's like hours or weeks out of date. And then you can imagine that the messages come in out of order. So all of these can be accounted for. We'll start with duplicated messages. What we do here is we generate an auxiliary table called processed entry, and we put a unique index on the entry ID so that you can't build 2 rows of a processed entry on the same entry. So now, whenever we're pulling from the queue, we consider, have we already processed a particular entry? If we have, we can just throw it away. If we haven't, we do the same, sum up the accounts, and this time, when we are summing all the entries together and inserting them into the table as one update, we also create a row in processed entries for each entry that we're working with. And since you can only create 1 row, if we get the same signal again, either the database transaction will blow up and we'll retry, or we'll catch it in the application logic by looking up the processed entry table, and we'll just drop the entry seamlessly. So this just gives you like your typical idempotency stuff. It's not that hard to cope with. The next case is missing messages. So I have not actually seen this happen in my queue, but we do have all of this like backup logic just in case. The idea is that you're going to periodically pull, say like every minute you have like a cron job that's going to look through your database. You just, in Rails at least, you add timestamps to all of your tables so you know when an entry was created, you know when your process entries were created in principle. What you do is you just look for all the entries who never got an account version and they're older than what you expect. So if you flush all your stuff every second and you expect that your database queue is going to give you your results within a couple of seconds, you can check to see anything older than a minute or 2 minutes as I have here. And then because your system is robust to seeing the same entry for processing multiple times from the previous slide, you can just confidently push those entries back into your queue, or you can pick them up at your queue polar level, however you want to process them again. Because the system doesn't care if it sees the same entry multiple times, it doesn't do anything bad, you can just push them back in as soon as you detect that they're not processed on time. Now, the third case is a little bit tricky, and it's out of order messages. And the ledger that we have described so far doesn't care if it gets messages out of order. You can just assign lock versions in the wrong order. But for the sake of example, and because this is like the trickiest case to deal with, we're going to add a new feature to our ledger, a new request from our product team, and then we're going to see how we can make sure that our system is still robust, even if it gets messages out of order. So imagine product comes to us and they want an undo feature. Maybe for some reason transactions get like rolled back or canceled. So when we get an undo signal on an entry, we just subtract its balance back off, and we still increment the version number of our account. So here we're creating an entry for 1,000. We get an account with balance 1,000 version 1. An undo signal comes in later. We subtract the balance back to 0, and the version has gone to 2. Easy enough. And this is like the happy path of the queue, where we get the create and then we get the undo. Now, our queue polar is aggregating together many entries. So if a user creates and then undoes a transaction very rapidly, you could imagine you get both the create and the undo within 1 batch update. In this case, everything's fine. Instead of getting 2 versions, we get 1 version. The balance doesn't change. Everything's fine. But the third case is that we just get them out of order. The undo comes in seconds, minutes before the create. And if we process this naively, we subtract the balance before we add it, and the account balance shows that it's negative, but it was never actually negative in any point in like real time. So this is a bug. Like the balance should never have gone that way. What you can do is extend the processed entries table, and you can add like a Boolean to it, created. So when we process an entry and it's a creation, we set that Boolean to true. When it's an undo, we set it to false. We change our unique index so that we can only process an entry ID with a given created at in one direction or the other. So this is just a compound index in your database where you say, I can process the entry twice, one's created true, one's created false, but I can't process 2 creates, I can't process 2 undos. So now, every time we get a message in the queue that's for an undo, we first ask the database, have we already created this entry? And we ask it just by querying the process entry table to see, like, for this ID, do we have a row for created true yet? If we don't, we just build the create entry. We know that you can't have an undo before you have a create. And so you can just inject it. And this, again, comes back to the guarantee we built for the first part of queuing, that you can get the same message multiple times. So item potency makes all of these other problems far easier to deal with. So in this case, we synthetically create the entry, and then we combine them into one, and it's like the second scenario that was happy. So those are like the different ways that a queue can give you surprising behavior. As you build into a queue, you also want to make sure that you are timing every step. You now have like an asynchronous machine with lots of different boxes, that diagram I showed you a little while ago. You're going to want to collect basically timestamps on every entry that you're processing through your system, and at every step along the way, you want to make sure that you're keeping up with what you expect. So we are using AWS SQS as our queue. Like, that isn't anything magical. Like, use whatever system you want. But SQS, we found, can take like up to 90 milliseconds to push data into it. And so we actually also have a step where we like asynchronously, outside of the web request, push our data into SQS. And we can do that confidently because we have that mechanism for, like, in case our async system drops the information before it gets updated, we'll just scan the database and pick things back up. But that like flexibility allows us to keep our web requests really fast. We just drop the intention to enqueue something into Redis in our web request, and then we can deal with like the SQS polling out of band. Between pushing data into SQS and then polling and getting it back out, that is the top chart there, and this is like Datadog dashboard for this queue. You can see that the median time is like 300 or 400 milliseconds, and the 99th percentile time is more like 1.3 seconds. So we try to make sure we process everything within seconds of when it comes in, and you can set up alerts if the system starts to fall behind by more than that. The second row of the chart, so the top row is between when a ledger entry is created and when that entry has a lock version assigned to it. That's like the latency and applying to the balance. The middle row is the time it takes between pushing something into SQS and getting it back out. And you can see that it basically matches the top chart because basically all the latency comes from just pushing in and pulling back out of SQS. The last one is after you get something out of SQS, how long does it take you to get the lock landed in the database? If you're transacting against your account too quickly and you start running into that hot account problem, this metric would blow up and it would start like going up to many seconds like we saw earlier with the hot accounts. So you can use all of these pieces of information together to kind of tune your system. You can reduce the amount of time that your queue poller is waiting to dispatch units of work until you start to see unacceptable like dequeue latencies. And you can set up all kinds of alerts around this so that you're making sure that your system is like actually landing the balances instead of like minutes or hours later. So on the topic of balances, it's important to keep in mind that we have two ways of storing balance in our system, and we always need to keep the entries as the source of truth. The entries describe like how all of the balance moved, and the account running balance is like a convenience feature so that we can write our database statements more efficiently. So I recommend you run SQL like this. I'll kind of walk through it in a second to make sure that your running account balance totals match the sum of all the entries. So this SQL has, first we use like a common table expression at the top here. We're adding up all the amounts on all of the entries, and so you end up with an account ID and an amount. And that amount comes from the entry sum. Then we join that to the accounts table on the account ID, and we just look for rows where the balances don't agree with each other. And so this is a fairly expensive query, but instead of running it every time a user transacts with your system, you use the account balance for the routine traffic, and then you run this, say, every minute. And if any of the accounts don't agree, you can instruct your code to stop using the account balance row for that entry, and you can fall back to summing up the entry accounts until you have solved your balance drift. So that's pretty much what I have for you guys. I want to kind of emphasize what I think you should do if you're interested in building a ledger. It is absolutely worth it to isolate your finances away from your domain objects. Money is complicated enough that it should be its own domain, and it's important enough. What you don't want is for you to have many different tables that all have like amounts interleaved with the business objects, and then you have to like join across lots of business objects and do some kind of reconciliation the hard way. The next point is row level locking is a hard constraint anytime you're using a relational database. Occasionally you get lucky, as with the ledgering case, and you have like properties that you can exploit to kind of get around that bottleneck. But anytime you do something that's like out of the ordinary, like the way that we're batching things together, it's going to add a lot of complexity to your system. So you need to be introspective about how much developer time, how much maintenance time, like do you really have appetite for doing this kind of stuff? It makes sense to do it in our case because we're trying to build a ledger for like lots and lots of customers to use, and some of those customers transact very heavily against hot accounts. It may not make sense to implement this kind of extra complexity for you, but I hope that the outline of how we went about this is useful for you, and that's all I have. So I think we have about 5 minutes for questions.
Curious how you handle the queue becoming overloaded because you're actually compounding that by pushing messages back.
Yeah, so the question is, how do we handle the queue being overloaded when we just continually push messages into it? So in the case of this system, what we found is if the queue starts backing up, we actually just spin up more and more queue pullers. The kind of bottom right block in the diagram that's pulling the queue, those can run independently from one another and dispatch multiple update jobs. You kind of have a limit of the kind of product of how many pullers you have and how often they're pulling. So you can tune those two parameters to either like push more throughput through your system, but at the expense of like now you're writing more rows per second to an account. So if you need to spin up lots and lots of those workers, you just make it so that they pull for longer each, so that each individual worker writes fewer writes to each row. But because there are more workers pulling off of the queue, you can basically scale it to an arbitrary amount of traffic up to the limit of AWS SQS, and that, as far as I'm concerned, is infinite. Yeah?
If you could build on any database technology today, and you wanted to eliminate the potential for drift and the potential for any kind of like
Yeah, so the question is, if I could build with any database technology and I wanted to make sure to categorically eliminate the problem of drift, which technology would I use? And I have to give you a pretty unsatisfactory answer, which is I'm kind of an expert in Postgres and Redis, but I'm not an expert in things like MongoDB or DynamoDB. I know a lot of people on my team have experience in Dynamo, and they think that that would be a good technology to move towards. We might do that at some point, but personally, I don't have the experience to give you a good answer. Yeah. In the queuing scenario, what? Yep. What if we had different amounts? Okay, so the question is, in the queuing scenario, if the undo comes before the create, what if the amounts weren't the same? So this is the more general problem with out-of-order transactions. I chose the example carefully so that was not a problem. The undos in the system I described are, by definition, the same as the create. And that means an undo carries all of the information necessary to proxy in that create statement that was missing when you do out-of-order processing. If you can't actually guarantee that, you will not be able to get by with a arbitrarily ordered queue. SQS offers a order guaranteed queue mode. It operates at about 1/10 the throughput as the unordered queue that we're able to use because of the nicer properties we have. So in the case where your system has to be processed in order, you can use a queue that's going to reliably give you data in order. And if that doesn't give you enough bandwidth, you can route your entries into multiple queues and then fan out into lots of queues and then fan back in to get the same kind of bandwidth. Fortunately, I don't have to do that. Any other questions?
I kind of have
Yeah.
one, but I don't know if it applies. I'm just thinking about how FIs and stuff have these periods like the end of the day or the end of the month. How does that play into the ordering and timing involved in this? I mean, you have to be more careful around those times?
Yeah, so the question is, a lot of institutions will have kind of end of the day processing windows where you'll get a deluge of transactions all in one big pile. So I don't think that this system needs any modifications to handle that kind of thing. The important consideration for your customer, you might actually have to scale up your background workers that are pulling data off the queue. But you could imagine you auto scale them every day at 11:45, and then you expect all this stuff to come in at midnight, and you can scale them back down at 1. But as far as the nice thing about this system, of course, is the exact ordering doesn't generally matter. And so when you get a thundering herd of traffic, maybe lots of the requests all get the same version on lots of different entries because you're processing bigger batches through your system. But as long as people are using the version numbers to track the kind of order in which things were applied, instead of trying to use timestamps, you shouldn't have any problems with ordering with big batches coming in.
Follow-up.
Yeah.
Does it really only matter if it's something like somebody's account and you don't want to fall under zero, basically, because you don't want to have money coming in and going out at the same time,
Yeah. So does it only matter if it's somebody's account and they have money coming in and going out at the same time? So when a user is spending money and we're trying to enforce their balance limit, of course we're still under that hot account limit where we can only process 20 or 25 per second. If a client has to do a nightly batch job where they put in a huge number of transactions, with this kind of system, if they have to validate the balances, they're going to have to throttle their traffic to stay within the limits. And they could just spray the API with as much traffic as they want. In practice, our API has a per account synchronous rate limit. So if you get close to that point where the transactions start to tend towards infinity, we just give them a 429, and in half a second, the the bottleneck will have cleared out and you can keep sending stuff. So we rely on the people who are sending us information to just gracefully retry when they see any kind of 400 response, and that's how we handle thundering herd. Oh, we'll let, yeah.
So when you're processing the messages of the queue, and you're essentially doing some sort of netting to understand what you want to commit later on as you're adding them up, what happens if you lose that memory but you've taken the messages of the queue? It's a system failure or whatever it may be. Then how do you go back to understand like what have you taken off, and then how do you update it?
Yeah, so the question is, what happens if you have some kind of system failure after you've pulled messages off the queue, but before you've landed them in the database, right?
Yeah.
Okay, so that gets us back into the scenario number 2, where of the 3 different queue failure scenarios, where a message is essentially never delivered. And they did deliver it to us, but we lost track of it and we didn't process it. That's functionally the same thing as the queue never telling us. So we just continually pull for entries that have been created in the system that haven't had a version assigned to them. And so if you lose track of the work partway through, you just pick it up again in a minute or something whenever your system detects that something is out of date. You might wonder what happens if you start to update the database, but it doesn't get all the way through. And the good thing is databases have our back on that. They are, like the ACID guarantees are atomic for the A and durable for the D. And so that means that either the entire database transaction lands and you have all of the processed entries, all of the new lock versions, the balance has been updated, all of that happens together, or all of it doesn't happen at all. And so if it doesn't happen at all, you just see entries with no version, you do them again. If it does happen, no problem. I think we'll take one more question.
Have you experimented with different serialization modes?
So the question is, have I experimented with different serialization modes in Postgres? The answer is no. Why don't we talk about that? All right, thanks so much, everybody. Oh. And of course, thanks to all the sponsors at the event. You should make sure to check out all of their booths. Yeah, have a great time.